Okay, so for the next few days, we are going to work on graphs of trigonometric functions. Okay, and just like with any other graph that we've talked about, we're going to talk about the parent function, and then we are going to talk about how we can transform it. Okay, our transformations are going to be the same no matter which parent function we're talking about. However, with sine and cosine, those stretches and shrinks, we actually have special names for that characteristic of the graph. So everything will be the same, but we're going to calculate it in a slightly different way because of the nature of the graph. Okay. So first I want you to think about your unit circle, right? You just went through the unit circle quiz. Already thought about it for a while. But if I want to graph y equals the sine of x, okay, I want to figure out what all of the sine values are at different angles, okay? So x is our angle, right? X, our input, is an angle. Y, our output, is going to be some ratio, all right? As we go along the unit circle, the sine of 0 is 0. Thank you. Okay, the sine of 0 is 0. So 0, 0 is a coordinate on the sine graph. Okay, and as we rotate around the unit circle, at pi over 6, the sine is 1/2. At pi over 4, the sine is radical 2/2. At pi over 3, the sine is radical 3/2. And then the sine of pi over 2 is 1. Okay, now, there are values in between all of these points, right? They're just not special, so we don't actually, like, draw them, all right? But there are coordinates there, okay? So between 0 and pi over 2, our sine values go from 0 and they increase to 1, right? And then as we rotate from pi over 2 to pi, our sine values go from 1 to radical 3/2 to radical 2/2 to 1/2 to 1. So do you see some symmetry in the numbers that I just pointed out, right? We go from 0 to 1, and then we mirror back all the way down to 0. Okay, and then as we rotate through from pi to 2 pi, we have sine values that are negative, right? At 7 pi over 6, we're negative radical 3/2. At 5 pi over 4, we're negative radical 2/2. 4 pi over 3, we're negative 1/2, until all the way at 3 pi over 2, we're negative 1. And then as we rotate all the way back up to 2 pi, our sine values increase back up to 0. Okay, blah, 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 blah. What does that mean? Let me show you a little graphic, which I had pulled up, and then I had to restart my computer, so let me get there. Okay. So right here, as you see this graphic draw around the unit circle, okay, it's plotting the sine values. Okay. Let you watch it for a little bit. It's kind of fun. Okay. So the sine of 0 is 0, so we're starting at 0, 0. The sine of pi over 2 is 1, so at pi over 2, our sine value is 1. Okay, remember we talked about how our sine values increase to 1, decrease to 0. Okay, and then from pi to 2 pi, we go in the negatives to negative 1, and then back up to 0. Right there. Okay. That, ladies and gentlemen, is the parent function for y equals sine of x. Now, what were to happen if we keep going around and around and around the unit circle? Are we going to get the same values? Yes. What's going to happen is this is going to go on forever and ever and ever. From 0 to 2 pi, we have this wave. From 2 pi to 4 pi, we have this wave. From 4 pi to 6 pi, we have this wave. It's what we call, you can either call it a cyclic function because it cycles, okay, or you can call it a periodic function because we're going to define what we call a period, and it happens over and over and over again. Okay. Now, you need to understand that the sine wave is going to go on forever like this in both directions. However, when we're thinking about the parent function, I would like you to think about this red piece that I have highlighted. So I need you to draw this in your notes. Y equals the sine of x. Those 5 points that I have highlighted are important. Make sure you have your x and y axis labeled so you can tell what those 5 coordinates are. If I were you, I would maybe make that red piece of the graph really dark and then lightly extend the waves so that you know that it keeps going on, but that red chunk is what I'm concerned about you know. In physics, have you talked about sound waves yet? Those of you in physics 1? No? Okay. You talked about them in physical science? No? Okay. When you get to the point that you talk about sound waves, trigonometric functions are related to sound waves. Okay, we are going to do the same thing to get the parent function for cosine. You ready? Okay. I'm going to put the unit circle up here again, and we're going to get our parent function for cosine. So here we go. Unit circle. Now we're looking at the x values, right? The cosine of 0 is 1. So the first coordinate on our parent function that we're going to focus on is 0, 1. Okay, we're starting at a different spot this time. And as you see, we rotate, as we rotate through the unit circle, okay? We begin at 1, at pi over 6, we're at radical 3 over 2, then we're at radical 2 over 2, 1/2, 0. So you can see that those values decrease until at pi over 2, we're at the coordinate 0, okay? Then we keep decreasing as we go from pi over 2 to pi. We hit negative values, negative 1/2, negative radical 2 over 2, negative radical 3 over 2, all the way to negative 1. Okay? And then as we rotate from pi to 2 pi, you see those same values, but we increase to 0 and then keep increasing back to 1. Now, do you see the same values in the cosine place as you do the sine place? At least not in the same spot, but you see the same numbers. Okay? Do you think there are going to be similarities between the cosine curve and the sine curve? Okay, there probably should be, right? They're coming from very similar numbers. So we're going to go to that graphic again here, maybe. Okay, but now we're going to do it for cosine. Okay, so as we go around the unit circle, the cosine of 0 is 1, so that's where we begin. We decrease to pi over 2, the cosine value is 0. Decrease, the cosine value at pi is negative 1. The cosine value at 3 pi over 2 is 0. And then the cosine value at 2 pi is 1. Okay? So the cosine parent function kind of looks like a valley, right? Okay. However, if we keep going, right, if we keep going around the unit circle in either direction, we're going to hit those same numbers in the same pattern. All right, so this is going to go on forever and ever in both directions. Okay? If you don't look very closely, this looks exactly like what I showed you up here, right? Here's the sine wave. Here's the cosine wave. The only difference is that we're beginning in a different spot of the wave. Okay? So our cosine curve, there we go. Our cosine curve looks like this. We start at 1, we dip down to 0, then -1, 0, and all the way back to 1. But it's going to go on forever in both directions, and the cosine wave and sine wave look the same. We're just starting at different places. So I want you to draw that red chunk of the graph, like you did before. Make sure you label the x and y axis. And then if you draw more than that red chunk, make sure that you have it colored in darker or highlighted or with colored pen if you have one, whatever. We're not actually going to graph these today. We're going to graph them on Monday, but what we're going to practice today is how to identify all the pieces of the graph. How do you know where the graph starts? How do you know how tall it is? How do you know how wide it is? Things like that. Okay? So there are 2 vocabulary words that we need to know. Okay? One of them is amplitude, and one of them is called period. All right, don't write it down yet. I'll let you write them down. But first, I want you to talk about with your prod the word amplitude. What does that sound like it could mean to you? All right, amplitude, pod 6. What do you think about the word amplitude? It sounds like the sound of something, right? If you play a guitar, like you plug into an amp, right? So amplitude kind of makes you think of that sound. Okay, pod 2. The height. Anybody else talk about that? Height. Okay. Amplitude does refer to the height of the curve. Okay, why did it make you think of height? Okay, Caleb?
Like changed how like the different sound.
Okay, so the an amp, right, is what you're thinking sound changes the sound, right? Amplitude changes the height of the curves, okay? And louder things are, the bigger they. I'm not sure. Amplitude does refer to the height of the graph, if we talk about the total height, it's actually double the amplitude. Okay, so what you're going to write down for me is amplitude is half the vertical distance between the highest and lowest point. Okay, so amplitude would be middle of the graph to the top, or middle of the graph to the bottom, or if you want to think of it as half of the total vertical distance.
So it's like the frequency.
Yes. Doesn't like the sound affect how like wavy the sound wave is? Yeah. Like lower sounds are like more stretched out, or higher sounds are like closer together, right? Okay. Versus like the frequency, like the sound would be more like the height of the wave. Okay, so our next vocabulary word is period. If amplitude is referring to the height of our graph, period would be referring to which characteristic? What? The wavelength. Okay? Wavelength is a great way to describe it. You notice that in each of our curves, they repeat over and over and over, right? And so one period would be the length from one point to where the graph begins to repeat. Okay? If you want to write wavelength instead of what I have written up here because that makes more sense to you, that's fine. Okay? But since our graph repeats over and over, a period is going to refer to the distance between one point and where it starts repeating that pattern. Okay, so we're going to go back to our parent functions, and we are going to identify the amplitude and period for our parent functions. Sine graph, our amplitude. Half the vertical distance from top to bottom. Okay, since we stretch from -1 to 1, that's a total distance of 2, our amplitude would equal 1. The period of this graph. I hear pi, I hear 2 pi. Take a point. Where does it start to repeat that pattern? Okay, here we make an S. At 2 pi, we start to make another S, right? So at 2 pi is where we would begin to repeat. Does that make sense, Eli? Okay. Let's look at cosine. What's the amplitude of y equals cosine of x? Also 1. Okay, we stretch from -1 to 1. That's a total of 2. Okay. And then the period. 2 pi again. Okay. So the amplitude of our parent functions are both 1. And the periods of both of our parent functions, 2 pi. I would like you to write these two equations down, okay? You're going to be able to graph the parent function, no problem. But I'm not going to ask you to graph the parent function very often. I'm going to ask you to graph functions that have been transformed. So, how do A, B, C, and D affect our specific parent functions? We're going to talk about that. Okay, so let's think back to chapter 1. That number in front of our function A, what kind of stretches or shrinks did it create?
Vertical.
Vertical. Okay, do you agree, Caleb? All right, if A affects our graph vertically, what characteristic is going to be affected? The amplitude. Okay? Whatever number in front of the sine or cosine is going to be your amplitude, as long as you take the absolute value of it. Okay? Amplitude has to be positive because it's referring to a height. It is possible for A to be negative. Let's talk about that. What does it mean if there's a negative in front of our function? There's a reflection, okay? And we'll talk about that more on Monday. But if we have a negative a, then the negative is giving us a reflection, and then a without the negative, that's going to give us the amplitude. Okay? B, when we have a number inside of our function multiplied to the x, what does that affect? Chapter 1. Horizontal stretch or shrink, okay? So if we're talking about horizontal stretch or shrink with a sine or cosine graph, what is that affecting? The period, okay? Now, since our parent function, both of them, have periods of 2 pi, it's probably an important number, right? If b is not 1, oh, whoops, I kind of forgot that I had this written up here. If you need to write this down, go for it. I got really excited about B. Okay, if B is not 1, then to calculate the period, we're going to take 2 pi divided by B. Two pi divided by b will take into account the horizontal stretch or shrink and help us find our new period. Okay? Now, C and D. C and D affect our graph how? Someone besides Caleb, who's answered all the rest. Thank you. Left or right shifts, right? Now, for sure, D is our vertical shifts, up and down, right? Now, that C inside, yes, is going to affect our graph horizontally, but that B is also affecting it. I don't know if you remember way back in chapter 1, but I told you you had to factor out a coefficient inside to get your horizontal shift to be accurate. So our shift would be C divided by B, comma D. And that is what we are going to call the starting point. Okay, we're going to use a method called the framing method to graph these. And the starting point is going to give us where we begin our frame. Yes? No, it's not a vertex. Okay, it is the starting point. Okay? I can't reiterate enough. The starting point does not mean that our graph starts there. Our starting point is going to be where we draw the frame to draw in our curve. Now, we're not going to do that until Monday, but I want to just give you a heads up. Okay? So all we're going to do today and your homework this weekend is you're going to be able to take a function, identify amplitude, period, starting point. That's what you need to be able to do by the time you get back on Monday. Okay? So, let's do some examples. Y equals 4 sine of x. Write it down. Okay. Lindsay A. What would our amplitude be? 4. 4. A is 4. Our amplitude is 4. Awesome. Okay. Maverick, what is our B value? What's the number in front of x?
1.
1. So that means our period would be what? 2 pi. Okay. If there is a coefficient that is 1 in front of x, our period is not going to change. Okay. Now, do you see a plus or minus? Do you see numbers added inside or outside of our function? No. So that means our starting point is going to be 0, 0. It's a nice one to start with, right? Next example. Y equals negative 3 cosine of 2x. Tegan, what would our amplitude be? 3. Thank you for saying 3. Okay, we don't worry about the negative for amplitude. However, what does that negative tell us? Grace W. Good, we're going to have a reflection. So I'll ask that you make a note to yourself that since A is negative, there is going to be a reflection. Okay, Nick, how are we going to calculate the period? 2 pi divided by b, b is 2, and so our period is pi. Okay. So we have a stretch of 3, so our cosine curve is going to be reflected. Our amplitude's more, so it gets stretched. Our period is less, so it shrunk a little bit. Okay, and then do you see anything added or subtracted inside or outside? No. So our starting point is 0, 0. Okay. All right, those were kind of boring examples. Let's step it up a notch. We'll start with the amplitude. Kira, what would our amplitude be? 2. 2. Okay. A is 2, amplitude is 2. Good. The period. How are we going to calculate the period, Haley?
Just take the 2
Mm-hmm.
and divide that by the 2 pi.
Okay, so we're going to take 2 pi divided by b. You said b is 2. So our period is pi. Okay. Now, Callie, what did I tell you that our starting point was going to be? Like in general. Like just CD?
It's C divided by B.
Okay, C divided by B, comma D. All right. Remember that it is BX minus C. Remember, everything inside of our parentheses ends up being opposite. Okay. So Grace F, how are we going to calculate the X coordinate?
Pi over 3 divided by 2.
Okay. So we have pi over 3 divided by 2. So our X coordinate is pi over 3 divided by 2, okay? Some of you can do this in your head. Some of you need a little bit of visualization. I'm going to remind you that we have pi over 3. When we're dividing by 2, that is the same as multiplying by 1/2. Okay? So the X coordinate of our starting point is pi over 6. And the Y coordinate for our starting point is what, Tiger? -2. Because of this guy right here. Caleb.
Is it possible to have cosine and cosine of x in one function?
I mean, it is, but that's nothing that we are going to graph. Like, anything's possible if it's thrown in an equation, right? But we are not going to graph sine x, cosine x together. Now, we might graph y equals sine of x and y equals cosine of x, two graphs on one, but we're never going to put them in the same equation. That's what you're asking. All right, last example before we part ways for the weekend. This first hour doesn't really seem like the weekend's that close. Okay, our amplitude, Chad, what would it be? 1. Very good. Okay, I do notice that there is a negative. Thank you, Chad, for not saying -1. So our amplitude's +1. Since there is a negative out in front, we do need to keep in mind that we will have a reflected sine graph. Okay. All right, Kiana, to calculate our period, what do we got to do? Okay, so 2 pi divided by b, b is 1/2. Okay, remember, when we are dividing, it's the same thing as multiplying by the reciprocal. Our period is 4 pi. So then for our starting point, C over B, comma D, the x coordinates. Marissa, help me out. Pi over 4 divided by 1/2. Which is what? Chris. Marissa, what do you think? Should pi over 4 be negative? Yes. Okay. And this is probably one of the hardest things to remember. Is that inside of our function, everything's opposite, right? So since this is plus pi over 4, our c value is actually minus pi over 4. So our starting point is at negative pi over 2, comma, the d value is what? 3. Okay. Questions before we, or not before we pack up? We're ready to roll here today. Okay, so you have an assignment. Well, please make sure that you complete your assignment, okay? To have the most productive lesson on Monday, I really need you to do your homework and come in here with an understanding of identifying amplitude, period, and starting point. Because we're going to start from there and build our graphs on Monday.